Hello, everyone. This is Naso Shalin, and today we're gonna review a couple of codes of nesting with CUDA. We're gonna start with this simple example of the nested hello word. So this is we have a kernel here. So this is a function, but it has its logic, and if you can notice here, we have a condition. If a number threat is smaller than zero, so we want to invoke the kernel. So here the main here we set up the size and block size and grade for the block and threads. So we create a blog and we create the grids. And here we're calling this uh, uh, kernel, which is this one here, that itself it calls the kernel. So that's why it's nested. So as we can see, we call it in here, and we're gonna see what happens. So we're gonna compile this code. Prepared all the uh, compilations for every single code. All right. So here we can notice, see the recursions, right? Hello world from thread zero, hello world from thread one, block zero, right? It goes two, three. It's actually a nested array, and then here hello world from thread zero recursion two and recursion three. So because here we have a conditions on how many recursions we want to do, but we see that how it's doing recursion here along. So basically, um, it's because we have a conditions here where we set up if the size of the block, and so this is what the condition is, and this is where we print in that. And here, for example, we show this is what showing is nested execution depth. For example, here is 2 and 3 and 1. So this is a small example with calling kernel with inside the kernel itself. This is another example here. It's called nested reduce. So this is implements of parallel reduction using nested kernel launches from CUDA kernel. This is the recursive implementation. So this is the host code in here. We have a logic, and as you can see, um, it returns this function itself, right? So this is the function, and return the function itself. So it's doing the same thing. It's actually nesting. So here at the kernel code, we set up here number threads and blocks, etc. We have a logic and on how to split on the number of global memory, and here this is where the colon is at, where we're calling the nested function. But the most important here is this kernel. So we have a logic. If the ID equal to zero, if is it, we call this one, and this one itself is calling itself in here. So after calling this, it'll return this one. So it's going to do a recursion as well. So we can test this one as well here. Here we have the CPU use shows and how many it took. So here the GPU neighborhood, it gives you the sum as well, and the GPU unless it gives you the sum. So everything, so the sum is correct in a whole different manners by calling the CPU, the GPU, and GPU nested. So then we're gonna go to the nested reduce 2. So this is an implementation of the power reduction using nested kernel launches from CUDA kernels. This version adds optimization on the work in nested reduce. So this is just an optimization to the previous code. And here we can see that the same thing. We have the function is calling is returning itself. So we have here reducing the neighbor pair implementation with divergence. This is a different kernel what we're gonna call, and then eventually we have this one here, and then eventually as well calling it in here the same thing but with a more optimized um, um, here a more optimized way by calling the GPU recursive reduce no sync. So here we have we have the condition to convert data pointer to the local pointer of this block. So this is where the optimization returns. So we converting the global data pointer to the local pointer of this block. So we can give it a try here. Let me tape it. All right. So here returns the CPU reduce, GPU neighborhood, nested no sync, and the GPU nested two. As we can notice, is returning all the sum, but with different timing, and we can see that GPU nested two, which is the most optimized one, is much faster. It is the fastest one. As you can see, the GPU nested is the longest one here, right? So here we have then it comes up um, the CPU reduce, then the GPU nested no sin, then the GPU neighbor. All right, so we've seen the comparative previously here. I mean, we just have a GPU nested with this time elapsing, which is this one in here. All right, so next one is to focus on nested reduce no sin. So this one is an implementation of a parallel reduction using nested kernel launches from CUDA kernels. This version adds optimization on the work in a reduced nested reduce. So here we have the same work and the same function reduce neighbor. It's pretty much the same code, but in here we have this function here right now. So here as well, this is where it, as we spoke before, convert the dot pointer to the local in this block. And we noticed here that before it was doing not bad at all compared to the nested one. So let's give it a try here. All right. So now we notice, so it's pretty much the same thing. And we see the CPU reduce is um, is doing as well great here. I think it's the best one, right? is the fastest one. No, not actually not the fastest one. It's a still better than the GPU nested no-syn, um, but it's performing well as well. So nested no-syn, it seems that it's faster than the GPU nested, right? So yeah, these methodologies. Um, so to conclude in this one here is that the most optimized one is the CPU is the GPU neighbor, and then it's the CPU reduce, then it's a then the GPU nest no sane, then GPU nested. So it's still better than the nested way, right? So now here we have another code. So this is different one. So this is a called a reduce complete enroll wrap. So this is the kernel for interleaved sum reduction. We're doing a sum reduction of floats with complete unrolling, and this is the unrolling eight. This is how we unroll. So this is the I mean the in a matrices. This is the specific items locations, and we're doing a summation here, right? And eventually we set up here the reduction of a complete unrolling. We set up the block dimension in here, and then we're doing the warp unrolling here by calling the threads. We're going by 32, 16, 8, 4, 2, then 1. And finally, we call the main code here. But the most thing to understand here is here we have allocated the device memory and copied the data from the host to device. Then we call, after copying the memory, we call the kernel in here. Then we copy the result in the memory, and finally we free it. So let's run this code in here. All right. So let's. All right. So here we're doing a summation correctly here after we get in total sum, and a very fast way as well. So this is the way I'm doing unrolling and using uh, the reduce complete unroll. This is a methodology of doing a summation. And then the next one is the reduce interleaved. So this is the interleaved here function. So he is doing interleave sum reduction. Instead of unrolling, he's doing now interleave. And it's pretty much the same concept like before. Um, we allocate the memory as before. In the latch data, we allocate device memory. We copy data from the host. But this reduced interleaved, it's different than before compared to a reduced complete unrolling, where here we did a summation of all specific items in one. So let's give it a try in here. All right, so here as well as doing the summation correctly. And as we can notice, compared to the other one, it's the same logic we get in different. um, different summation, and we're gonna come up here eventually now with an exercise to compare why that's happening. But before that, let's as well come with this reduce integer. So this is implementation of the interleaved and neighbor pair approaches to parallel reduction in CUDA, and the sum of operation is used as a variety of optimization or parallel reduction aimed to reducing divergence, as we have a condition f and of f. So here to reduce the diversion, we use this methodology is the recursive reduce. So here we implement the neighbor pair implementation with divergence. And here we, as before, we convert global data pointers. We have the boundary track. Here we have a reduction in global memory. And here we synchronize. So here what happens in this kernel reduced interval leaved. So this is where we have this the divergence, and we want to reduce it using this function of reduce a neighborhood. So let's give it a try. Let's compile it. All right. So here we have seen the differences between interleaved and unrolling 2, unrolling 4, and unrolling 8 before we did unrolling 8, unrolling warp 8. As you can see, uh, the best one ever, it seems like it's the counter roll. It shows us here. Then the worst one here, and we can see they all get optimized, but in different sense. And on Warrior 4, it took much longer, even than on Warrior 8. But we have a whole summation altogether. But as we can see, on Warrior 4 actually has less of the grids. Probably that's why it's been taking much longer. All right, so the next one, let's talk about sample divergence. So the sample divergence, it's demonstrate divergence code on the GPU and its impact on the performance and CUDA metrics. So here we have the the kernel here, math kernel. We have its logic, and we have a math kernel 2, and it has its logic. And we have math kernel 3 with its logic. And then we have this function, it's called warming up. So it has its logic. But here, when we call them, when we call these functions, um, so basically they're all different kernels, but we're calling them uh, eventually here at the main. So yeah, so here's there we go. So this is we're calling them in a warming up grid, and we call them math kernel one. So we're calling them one after one, and basically what we want to do here is demonstrate divergence code. That's the purpose of this code. So let's give it a try. All right, so we see it here right now. it it called them as in order of the cardinal, and it shows that they all have uh, they have all pretty much almost the same logic but different divergence. That's where there is a different differences in time elapsing. However, the Cardinals 16 and 1 were similar, so probably there is um I think if you remember, yeah, I think it's they different, but there is a different on the condition itself. That's what is making the time elapsance difference. So here, let's try up separate divergence too. So this is separate divergence. So this is pretty much the same code, right? It's just more and more optimized way, and we can even try here. What's going on here? All right. So we've seen right now that the time it took that fast, and we're gonna look why it's doing that. So the difference in here is the way that we set up the pointers and allocate the memory. That's why it's being like much faster than the previous one. So now let's go to the sum matrix here. So this example implements a matrix element wide addition on the host and GPU. So the mass matrix on the host iterates over the rows and columns for each matrix, adding elements from A and B together and storing the results in C. And the current offset in each matrix is stored using a pointer arithmetic. So this is the host code here. We have this logic. Then we have the sum matrix. This is just two matrices, and we have sum up. And here we're checking the result with this function. Here we're calling it kernel. We set up the block dimension and threads. And here we call the code. So here as well, we set up the size of a matrix. Here we allocate the host memory with this code. Here we initialize data host, and here we add the matrix host side for result checks. And then after doing magic, we malloc the device global memory. Here we set up the CUDA malloc memory. Here we transfer data from host to device, then invoke a kernel on the host side, and here we execute the kernel. So this is the kernel calling invocation in here. Then after that, we copy the kernel result into the host side, and we free the memory eventually. So let's see how that goes after calling that. Well, it seems that it's been taking forever. All right, so let's then go to the sum matrix to the optimized way. Yeah, seems that the CUDA couldn't process it. It got kind of stuck. Okay, so now after seeing that, uh, there we go. It couldn't function properly. So Yeah. Thanks for watching this video. And the next video, I'm gonna discuss on resolving these two exercises and 5 and 6. Thank you.